Welcome to this explainer. Okay, so have you ever caught yourself staring at your computer screen, just kind of wondering how on earth it actually understands what you want it to do? Well, today we're going to demystify exactly how we bridge that massive communication gap between human thought and computer execution. It's a seriously fascinating journey, and by the end of this, you'll see exactly how the digital world translates our ideas into actual action. Let's dive right in. So, let me ask you a quick question. If you speak to your computer right now in English, or maybe Hindi, or French, does it understand you? I mean, naturally, the answer is a resounding no. We use language to express thoughts, ideas, and really complex emotions to one another. But computers, they are completely oblivious to human languages. And this sets up our foundational conflict. To a computer, our nuanced words are literally just noise, because they only speak machine language. Just notice the stark contrast here. On one side, we have human language, right? It's complex, nuanced, filled with context and emotion. But on the flip side, we have computer language, a rigid, endless sea of binary ones and zeros. This isn't just a slight difference in dialect, it's a profound communication divide. The hardware of a computer processor only responds to electrical signals, represented by these zeros and ones. So the big question is, how do we actually get from a human idea to a binary execution? Well, that brings us to our essential tool, computer language. Basically, a computer language is a structured medium used to communicate precise instructions to a machine. It tells the computer exactly what to do, how to do it, and when to do it. Take a look at this really simple Python command, print hello world. Now, that's readable for us, right? But it contains specific rules that will eventually tell the screen to display that exact message. It's kind of our way of reaching across that massive divide. Section 1. The three language bridges. To really understand how these computer languages work, I want you to imagine a massive, deep canyon separating us from the computer's processor. To cross this huge divide, we've built bridges. And in the programming world, there are three primary levels of computer languages, which we can totally think of as three very different types of bridges. It's the classic rule of three: low-level, middle-level, and high-level languages. As we move from low to high, the languages become way less like the computer's binary and much, much closer to our human language. To make this super easy to grasp, we're going to compare them to a rope bridge, a steel bridge, and a futuristic sky bridge. Let's look a little closer at the first one. First up, low-level languages. Think of this as a terrifying swing rope bridge. It's directly connected to the raw hardware way down on the canyon floor. There are basically two types here. First is machine language, which is just pure binary, ones and zeros. The computer understands it perfectly, but for us humans, it's incredibly difficult. The second is assembly language. Notice how instead of just ones and zeros, it uses short codes. We call them mnemonics, things like add, sub, or move. So it's a bit easier than pure binary, but make no mistake, it's still a treacherous rope bridge meant mostly for the hardware locals. Next, we upgrade to the middle-level language, like C. Imagine this one as a sturdy, reliable steel suspension bridge. It actually has a paved road, making it much safer and way easier for humans to cross than that shaky rope bridge, but it still gives you direct, low-level access to the hardware deep down in the canyon if you ever need it. C language perfectly bridges the gap, allowing programmers to write understandable code while still controlling the computer's memory and processor directly. And finally, we have high-level languages, like Python, Java, and C++. Picture a completely smooth, futuristic automated sky bridge. This bridge is the furthest away from the gritty hardware and the absolute closest to natural human language. As we saw earlier with our Hello World example, it is incredibly easy to read, write, and maintain. Because it's so automated and user-friendly, high-level languages are what most modern software developers use to build the apps and programs we rely on literally every single day. But wait, if we're up on this automated sky bridge writing code using English words like print, and the computer at the bottom of the canyon only speaks ones and zeros, how does the computer actually understand us? Well, we need guides. Section 2. Meet your translators. So a translator is basically a software program that converts our human-readable code into machine language. And just like we have three bridges, we've got three main types of translators. First up is the assembler. Think of the assembler as the rugged local guide stationed specifically down at the low-level rope bridge. Its one and only job is to take those assembly language mnemonics like add and sub and decode them straight into the binary machine code that the processor can actually execute. Next, we have the compiler. Imagine the compiler as a super meticulous bridge architect. Before you're even allowed to take a single step across the bridge, the compiler takes your entire travel map, your whole source code, and translates it all at once into a complete machine code file. Languages like C and C++ use compilers, and because all the translating is done before the journey even begins, the final program executes incredibly fast. Then we have the interpreter. Unlike the architect, the interpreter is like a live personal translator walking right beside you on the bridge. Instead of translating the whole map at once, it reads and executes your code step by step, line by line. Python is a famous interpreted language. Because it translates live, if you make a mistake, the interpreter just stops and tells you immediately, which makes it absolutely fantastic for beginners trying to spot errors. Let's just do a quick comparison of our two main high-level guides. The compiler takes the whole program at once, resulting in much faster execution for the user. The interpreter, on the other hand, translates line by line. Sure, it might be slightly slower to execute, but it makes debugging, finding and fixing mistakes, significantly easier for the programmer. Depending on what you're building, you'll choose the guide that best fits your journey. So, we have our languages and we have our translators. Let's map out the complete step-by-step journey across our metaphorical bridge. How exactly do we get from human thought to computer action? Section 3, the code conversion journey. This right here is the absolute foundation of programming. Here's the exact path. Step 1, the programmer writes the source code in a language like Python. Step 2, we hand that code over to our guide, the translator. Step 3, the translator converts it into binary, machine code, and feeds it directly into the computer's CPU. And finally, step 4, the CPU executes those instructions and generates the output, whether that's, displaying text, loading a web page, or moving a character in a video game. Section 4, hazards on the bridge, errors and debugging. Now, of course, no journey is perfectly safe, right? Mistakes happen, especially when you're writing really complex instructions. These hazards are what we call errors, and keeping with our rule of 3, we can categorize these hazards into 3 specific types: syntax errors, runtime errors, and logical errors. Understanding exactly which hazard you're facing is absolutely key to successfully crossing the bridge, so let's break them down. First up is the syntax error. This happens when you violate the grammatical rules of the programming language. Imagine this as a structural violation on the bridge itself, like you literally forgot to build a step. For example, if you forget a closing bracket or a quotation mark in your code, the translator gets completely confused. Because the structure is broken, the program cannot even start. You have to go back and fix the step before you can walk on it. Next is the runtime error. Now, this one happens while the program is actually executing. The syntax was fine, the program started up, but then it hit an impossible instruction, like trying to divide a number by 0. Think of this as the bridge suddenly collapsing under an impossible weight mid-journey. The program starts running fine, but then just crashes unexpectedly. Finally, we have the logical error. Now, what's really interesting about this one is that it's the trickiest hazard of all. There are no missing brackets, and the bridge definitely doesn't collapse. In fact, the program runs perfectly from start to finish. But the output is completely wrong. It's exactly like safely crossing the bridge, only to realize you walked to the entirely wrong city. The computer did exactly what you told it to do, but your human logic was just flawed from the very beginning. So, how do we actually deal with these hazards? Well, we use a process called debugging. Debugging is the process of hunting down and correcting these errors to ensure your program is accurate and reliable. Whether you're fixing a missing quotation mark, patching up a runtime crash, or totally rethinking your logic to make sure you get to the right city, debugging is an essential survival skill. In fact, pretty much every programmer on Earth spends a massive portion of their time just debugging code. Wow, we've covered a lot of ground today. We established the divide between humans and computers, explored the 3 bridges of computer languages, met our trusty translators, walked the entire journey of code conversion, and learned how to survive the hazards of errors through debugging. The absolute crucial point to take away here is that computers aren't magic. They just require the right bridge. Now that you understand exactly how these bridges work, the only question left is, what are you going to build first? I really hope this explainer sparked your curiosity to start writing your very first lines of code. Until next time, keep learning and keep building.